Hi, I'm Abhishek. In the previous video, we have created the block design and exported the overlay files. So in this video, we'll use those overlay files to create a Python program to control the CB4CLED using the Jupyter Notebook interface. So before that, we'll set up the PYNQ-Z1 board, then connect it to the computer and access the Linux terminal, then set up the Jupyter Notebook interface. To get started, we need to flash a microSD card with the PYNQ-Z1 image. For this demo, I'm using version 2.1. If you have already have a preloaded image, then you can skip this first step. So you can download the image from this link. It's a PYNQ.io documentation page. So the PYNQ-Z1 board Digilent. So you can download this image, and I've already downloaded it. So you can either use Win32 Disk Imager, Rufus, or Balena Etcher, which are all image writers, and it's a straightforward process of writing the image into the SD card. So the next step is to insert the SD card into the card slot at the back of the PYNQ board. Then you can connect to the computer using the micro USB port, and also a Ethernet cable with one end to the Ethernet port on the board and other end either directly to the computer or to a router. So this diagram shows the ports of USB, Ethernet, and micro SD card at the back. And before turning on the board, we need to set some jumpers. So in the JP4 port, you need to connect the SD pins, which indicates that the processor should boot from the SD card. Then the other jumper pins near the power switch to indicate the board should be powered on using the micro USB. And then you can turn on the board by using the power switch, the bottom left. So as soon as you turn on, the red LED near the power switch will light up indicating the correct power supply. Then the green LED, that is LED 2, it will in the middle will light up indicating the board has started to boot. So the 4 LEDs near the switch and 2 blue LEDs will flash once the board is operational. So assigning static IP, so you can skip this step if you are connecting the board to the router. If you directly connect the board to the computer, then you need to assign a static IP for the Ethernet in order to access the Jupyter Notebook. So for that, I'm using a Windows machine, so go to Control Panel, Network and Internet, Network and Sharing Center, and go to Ethernet, Properties, and scroll down to Internet Protocol version 4. And you need to use the following IP address, and the IP address of you can set the IP address to 192.168.2.1. The IP address of the PYNQ board is 192.168.2.99, so the IP address to be set here should be in the same range, and the subnet mask will be autofilled, and then click on OK. OK, close. So we have set up the assigned static IP. For Mac and Linux, you can follow the steps provided in the PYNQ documentation page. So now we can proceed to accessing the Linux terminal of the PYNQ-Z1. There are two methods. First is using a secure shell. So for that you need a SSH client called PuTTY. I've already installed it, so I'll open. So this is the interface for PuTTY. In that you can, for the first method we're using secure shell, so select the SSH, then give the IP address of the target, that is the PYNQ board, which is 192.168.2.99, and leave the port to 2020 and click on open. So the username and password for the board is Xilinx. We have successfully logged in and accessed the Linux terminal of the PYNQ board. You can check that using the uname. And the second method is using a serial connection, that is through USB and COM port. For that, you need to open the device manager and go to ports. Here you can see USB serial port, which is on COM 8. So we can again open the putty. I'll close this. And now it's serial connection this time. And the serial line should be the port name, which is COM port COM 8. And leave the speed to 115,200 and click on OK. So we need to press enter to get an input from response from the board. So we are again now accessing the Linux terminal, but this time through the serial port. So next we can get started with the Jupyter notebook. So we have set up the static IP and we have connected using the Ethernet also. So now if you're connected the board directly to the computer, then you can go to this address, that is IP address of the PYNQ board and port 9090. If you have connected to a network router, then you can give the name of the board PYNQ and the port 9090. So now I have directly connected to the computer, so I'll be going into the first link. So, yeah, this is what these folders will be provided by Xilinx, and you can go into the Python notebooks to check out the basics. And if you go into logic tools, you have few sample programs, Boolean generator, FSM generator, Python programs, which uses an inbuilt overlay. So for our counter program, I'll create a new folder and rename it to CB4CLED and go into that folder. Now we need to upload the overlay files into this folder, for which we can go to the project folder. I've copied all the 3 overlay files from the respective locations into the main project folder. So to copy this into the Jupyter notebook, we just need to select and drag drop into the folder and click on upload. So yeah, we have uploaded the overlay files to the storage of the PYNQ-Z1. Now we can click on new and Python 3 for a new Python notebook. So we need to import that overlay files into the program application. So for that we need an overlay class. So we can import that overlay class from PYNQ library. Now we can reference the bitstream files and create an overlay object for that. I'll name it as counter equal to overlay. And we need to give the same exact name which we give for the bit file. So which is CB4CLED design. CB4CLED design dot bit. So it has been successfully imported. So we can check the input and output signals of the overlay by using the ipdict.keys function. So here is all the 9 signals of the counter are present in this overlay. So we have instantiated the CB4CLED overlay. Then we have checked the signals. Now before writing or reading the signals, one thing we can do to make it convenient for us to reference the signals is either you can simply do by counter.ce write 0, 1. This will work, but for convenience I'll create objects that corresponds to each signal. So for example, CE equal to counter.ce. So like this I can create objects for each signal, so I can easily reference the signals using these objects. Okay. So now we'll try writing into signals. For example, I'll write the value 1 into load signal. So for that I can put load dot write, and the first argument of the write function is the offset, which is usually 0. Then the second argument is the value to be returned. So in this case I want to write high value, so it's 1. So the value is written into load, and we can read the value using the read function. So I'll read and print the value, load dot read. So we have written 1 and read it. And if I want to set it to 0, yeah. So I've written a short program, short line of codes, few line of codes to reset the counter and set all the signals to default values, which is writes the load to 0, chip enable to 0, up counter to 1, up signal to 1, and reset to 1, then does a clock pulse, and then sets the reset to low, and again a clock pulse. So yeah. Then we can load data into the counter using the load dat signal and the load signal. So I want to write the value 4 onto the counter. For that I need to send the value 4 through the load dat signal, then assert the load signal, then do a clock pulse, then I have to set the load signal to low again. And to set the counter to count upwards, you can write 1 to up signal and do a clock pulse again. And I'll try to read the count value to check whether the value 4 has been loaded properly. Yeah. So now this is the code to run the counter and read the outputs. So first what it does is asserts the clock, then asserts the chip enable, reads the CEO output, then it sets the clock to low, then again the rising clock edge, then sets the chip enable to 0, and then it again gives a clock pulse, then reads the TC and count values, then writes the clock to 0. So I'll run it. I'm using shift and enter to run. So the count is 5, which has incremented from the previous value of 4. So if I run it again, the count has increased to 6, 7, 8, 9, 10, 11, 12, 13, 14. So when the count has reached the maximum value, the terminal count TC value has been asserted. So if I again run it, the count will be set to 0, and since the TC in the previous clock cycle and the count chip enable is asserted, the CEO value is asserted this time. So this keeps on running. How many ever times we rerun the cell. We can also use for loops to run the program as required. So yeah, I've covered the creation of overlay files and the setup of PYNQ board, the Jupyter notebook interface, and a sample Python program to control the CB4CLED. So Thank you.